Yeah.
You're good to start.
All right. So tonight we're going to be covering some reverse engineering. Essentially, we're going to be looking at compiled code at binaries. We're going to be taking them apart and we're going to be trying to see what they do without actually running them. So if you need internet, we do have available that you can connect to, although I assume everyone here should have access to internet. If you do, just get Alistair or someone to help you. Or if you don't, before we get, yes, my mic is turned on. Is this better? Yep. Okay, cool. So before we get started, I do have to introduce myself, unfortunately. So I am a third year in a cybersecurity degree, so I'm set to graduate at the end of the year. I've been a junior cybersecurity engineer for a few months, and then I was promoted to just being a regular cybersecurity engineer. And I've competed in national and international robotics competitions. Why I mention that is because that's where I learned C. That's where I started to learn about how computers work at the low level. And cybersecurity is such a broad topic that you can find anything that you're interested in, and it will show up in cybersecurity. Find something you like, nerd out about it, and then just look for where it is in cybersecurity, and you'll just be able to do it. We do also have, with GitHub Education, for students, you can sign up for GitHub Education and you get a bunch of access to courses and different resources that are all free. So definitely make the most out of those. So what is reverse engineering? Fundamentally, it's a process to figure out what something does or how it was made. If a UFO falls out of the sky, people will reverse engineer. What is this? How was it made? How does it work? Was it meant to fall out of the sky? Maybe. We're only going to find out by reverse engineering it to find out what it's supposed to do. And there is a famous example of reverse engineering. During the Cold War, the Soviets had developed a new fighter jet called the MiG-25, and this jet terrified the West. American intelligence thought they had no way to counter this futuristic jet. The F-15 was in development at the time, but its requirements were increased so that it would be able to compete with the MiG-25. However, in 1976, US intelligence borrowed a MiG-25. The Soviet pilot defected and flew his plane to Japan, and then the Japanese authorities brought in US intelligence. The Soviets were furious. They demanded their plane back. But US intelligence, they did some reverse engineering. And about 20 days later, the Soviets got their plane in pieces. It turns out the MiG-25 wasn't much of a threat. And because the US took it apart, like in pieces, they got back boxes of their fighter jet. The US realized this isn't really a threat, and the F-15 probably could have taken it. Now, in cybersecurity, we reverse engineer to defend largely against malware and new attacks. We need to understand what they are and how they work. In 2017, there was the WannaCry ransomware attacks, and this ransomware was devastating, especially in the UK. It took out large chunks of the NHS, which is like their version of Medicare. What this malware did was it would spread throughout the network, encrypt systems, and just keep spreading. So it was a real threat, and security researchers started to reverse engineer this malware to stop it. And they realized what it would do, it would try to connect to some website that didn't exist, and then it would encrypt your system, spread to other systems, do all the stuff we'd expect ransomware to do. But why was it trying to connect to a website that didn't exist first? The security researchers created this website so that the ransomware would connect to it. They were just hoping to find the connections, but it turns out this was the kill switch for the ransomware. It stopped spreading. If it could connect to this website, it would render itself inert. And it's only by reverse engineering this ransomware that the researchers were able to actually find out what it did and how to stop it. There are two main types of reverse engineering. There's static analysis, which will be the focus of tonight, which is where we inspect an application without running it. So this means that we look at the data, but we don't actually run it. We don't know what the application will do. Then there's dynamic analysis, which is where we run the application. And you can think of this like conventional debugging. You have breakpoints, you can stop the code, start it, you can inspect the memory, and you can alter the memory. Now, why would we use static analysis? Let's just imagine you have been sent a file, freemovie.mp4.exe. Do you open it? Think about it. What are our options here? On one hand, we get to watch a free movie. That's pretty good. On the other, some guy's going to start mining Bitcoin on our computer. Free movie, Bitcoin miner. It's a toss-up. We could reverse engineer this. We could use static analysis to see what this executable does. You could also just delete it. That is also a perfectly valid option. So we have a bit to get through tonight. We'll cover some background knowledge, so some binary, bitwise operations, and some basic C. And then we'll cover reverse engineering in depth, and especially ghidra, which is the tool we'll be using for tonight. And then we have a CTF. So we'll be solving challenges and winning prizes. Just so I can get a rough idea, just by a show of hands, who's done a CTF before? All right, good. So that's quite a few of you. And who's done any sort of reverse engineering before? Okay, a few less of you. So that's good. For those of you that have done this, we'll just be seeing this sort of a review of the fundamentals. And for those that haven't, we'll just be covering some of the skills and tools that we'll need before we get into the challenges. We do have prizes for the CTF. So we do have a GitHub plush and some Try Hack Me vouchers for the winners. And let's get started with the background knowledge. So computers count using binary. Decimal, what humans think of as counting, we just have the digits 0 to 9, but with binary, you just have two digits. It's 0 or it's 1. Those are your two options. Binary numbers are how computers store numbers, and more specifically, computers store them as bytes. One byte has 8 bits. Each bit is either a 1 or a 0. And sometimes when we see binary numbers written down, they'll have a 0B in front of them so that we know what we're looking at. If I just see 1, 0, is that decimal? Is that hexadecimal? Is that binary? I don't know, and its meaning changes. So sometimes it'll have a 0B. This isn't a standard, though. You'll quite often see binary numbers with nothing in front of them, and you'll just have to sort of infer that this isn't some weird number with only 1s and 0s. It is binary. So when we look at a byte, each bit has a number to it, and because computers start counting at 0, the smallest bit is known as bit 0, and then each bit is bit 1, 2, 3, 4, 5, and so on. Each bit, instead of decimal where it's 1, 10, 100, and so on for each digit, in binary it's 1, 2, 4, 8. It doubles each time. If we look at a number like 43 in decimal, it's read as 0 hundreds, 4 tens, and 3 ones. In binary, though, that would be 101011, where it has 132, 016s, 18, 04s, 12, and 11. And if you sum up all of those, then you'll get to 43. Now, we have math operators that we can use with our numbers. Those are great. They work on the number itself. So that's plus, minus, divide, multiply. We then also have bitwise operations that just work on the bits of a number. So math operators work on the number. Bitwise operations work on the underlying representation of that number. There are 3 main ones. The first is a bitwise AND. If both inputs are 1, the output is 1. And there's a bitwise OR, where if either input is 1, the output is 1. And then there's bitwise XOR, which is if only one input is a 1. So XOR is used quite a lot in ciphers because it's one of the few bitwise operations that is completely reversible. So if I XOR two numbers together, I can then XOR them again to go back to my original number. Now, there's also hexadecimal that's closely related to binary. It's a more efficient way to represent a byte. It's base 16, and we can count 0 to F. And hexadecimal, it starts off like decimal for the first 9 digits, but once we get to 9, then we count and we say, okay, well, A is 10, then B is 11, C is 12, D is 13, E is 14, and F is 15. And the reason that we do this is a more efficient way to read a byte. So if we look at a number in decimal, so 129, that's 3 digits to see it. But in hexadecimal, that's only 2. That's just read as 81. So 8 16s and 1 1. And to represent a byte with hexadecimal, first we break the byte in half. Now, does anyone know the term for half a byte? If I am eating a sandwich, and I'm not that hungry, so I only have a little bite. I've not had a bite, I've had a nibble. It is a nibble. Half a byte is a nibble, and it's also spelled with a Y, like how byte has a Y in it. So we take our 2 nibbles, each has 4 bits and can store 0 to 15 or 0 to F in hexadecimal. And we convert that number into hexadecimal, into its digit. And usually hexadecimal is written with a 0x. This is much more of a standard. Binary is kind of a suggestion that it should start with a 0b. Hexadecimal will nearly always have a 0x in front of it. And this is how we'd represent a binary byte in hexadecimal. So we break it into half into our 2 nibbles. The left nibble has 2, so that's just 2 in hexadecimal. The right nibble has an 8, a 4, and a 2, so that's 14, and so it's E in hexadecimal. And we can then convert hexadecimal to decimal because we have 2 16s, 32, and then we have 14 ones. So if we add that together, we should get 46. That's all we need to cover about binary. The main thing is you need to know that that's how computers store numbers, as just bits and bytes, and hexadecimal is how we'll be looking at a lot of bytes because it's just a more efficient way to look at them. Now, we will cover some basic C, but I am assuming that most people have written some code before, so you are familiar with programming, you just might not have seen C before. C is one of the oldest languages still in use. Most operating systems are written in C, and C is not a memory-safe language. C gives the programmer control over memory. It's not that managing memory is hard, it's getting it wrong is really easy, and a lot of people do, but that's great for us, that's job security. C only has a few data types. It's a really simple language, and we don't actually need to be fluent in C to reverse engineer. Most of the time as we're reverse engineering, we'll be looking at code that's in C, but we don't need to read C. We just need to know a few keywords and how C looks, and we'll be able to figure out what the code's doing. So if you know another programming language, C is no problem for you. If you've done Java, then C is very similar. If you've done Python, you'll get the hang of it, but a few things are slightly more different. So for our data types in C, we have an int, which is a 32-bit integer. Technically, this is platform specific. It'll be 32 bits, and this is just any whole number. Then we have a long, which again, platform specific, it'll be 64 bits. Unless you're using a computer from over 20 years ago, if you're trying to reverse engineer for the Commodore 64, this won't be right, but it will be 64 bits. And this is like an int, it's just a whole number, but this is a bigger whole number. This can count higher. Then we have a char, which is an 8-bit character. And this can be signed or unsigned. If a programmer just wants to have a byte to work with, they could just use an unsigned char, and then that gives them their byte that they can use. And then we have floats, which is just any number with decimal points, 3.14, 2.7, 553,002. Any number with decimal points is fine. And there's also a double, which is like a float, but it's bigger and it has slightly more precision. But we've just made a big jump. Can anyone tell me where we've just jumped with our logic? So computers just have bits and bytes, right? That's how they store numbers. Just bits, just bytes. Where did we get data types from? So storing like numbers, like int and long, that makes sense, right? We're just like storing whole numbers. But where did we get floating point numbers from and characters? How are we storing those? Because it's just bits and bytes on our computer. And it's because we don't actually have data types. Data types are a myth. That's just something that we've come up with as programmers to make it easier to work with computers. But bytes are just data. This byte is just data. It has no data type. This is just the ones and zeros that make it up. Its meaning changes based on how we interpret it, and we interpret it with its data type. So as a character, that's a capital L. As an int, it's 76. As a float, it's 1.06 to the negative 43rd. And as an instruction, it's an absolute jump on a 6502. But you get the idea. All of this, whether our computer executes it as code or sees it as a number or a letter or a decimal value, all of that is based on the data type that we use in our code. To the computer, it doesn't matter. It is all the same. So to summarize this, the data type just tells us how to use the data, but it doesn't actually affect the underlying data. So in C, an int or long just uses the data as an integer number, and this will be in 2's complement. A char treats the data as an ASCII encoded character, which is only 7 bits. So there is actually a spare bit to play with for ASCII. And a float treats the data as an IEEE 754 floating point number. If that means something to you, good for you. There's also arrays in C, which are another thing that we need to know because they work a bit different in C to other languages. So in C, arrays are pointers. So like most other languages, arrays start at 0. And we create an array with this syntax. So the data type, how we want to treat the data, in this case an int, then we're calling it R. We have our square brackets, and then we set it to a list of numbers. And if you care, this array is on the stack, so we can't change its size at runtime. And this is how that would sort of look. So the first index, index 0, stores the first value, and so on up to the length of the array. But we can also create an array using something called malloc, which is a memory allocation. It returns a pointer to the start of the memory. Essentially, what malloc does is it just says, hey, you can fit an array in memory here. It doesn't do anything else. It doesn't initialize that data. That will just be random garbage in your array that you will have to clear yourself. To create an array with malloc, it looks a bit different. So it's int asterisk, which is a pointer called R, equals malloc, and then it's the size of the type we're storing, times by how many of that thing we want. And so malloc will just give us a block of memory that is that big, and it tells us where that is. So malloc gives us data on the heap. We can free this and malloc a new data. We can change the size of this array. And malloc returns that pointer to the 0th element. And then we can index based on there. So the array +1 is the next one, +2, +3, and so on to access all of the elements. It's important to note this is not bounds checked. No arrays in C will actually check if you're accessing out of bounds. If you're writing to memory that you do not have access to, that's fine. C does not care that you're doing that, which again, more job security for us. Now let's talk about reverse engineering. We've got through sort of the basic stuff that we do need to know that we will be using, but this is when we can really get into the fun stuff. So in our case, reverse engineering is analyzing an application to see what it does and how it does it. So we're focusing on static analysis, which is inspecting an application without running it. This could be decompiling the application, inspecting the binary data of the application, or if you're a psycho, even just reading the machine code to see what your computer would do when it is given this executable. Now, compared to dynamic analysis, we won't be covering dynamic analysis, but it's good to compare the two. Some malware detects that it's being analyzed, and so it'll change its behavior. It'll see that a debugger has been attached, and so it will then behave inert. Static analysis stops this because the malware never gets the chance to run and to hide what it would do. However, some malware is so heavily obfuscated that the easiest way to see what it'll do is to just run it and see what happens. Of course, people use sandbox environments, which some malware can detect, and so there's kind of there's a trade-off. Which one do you want to use? Do you want to use static or dynamic? And usually people will end up using both. Now, we've been throwing around this term of binary for an executable, and let's actually see what does binary mean. So a binary is just an application that's being compiled to an executable format. So that's ELF on Linux or a Windows PE file on Windows. And on Windows, they'll often have a .exe extension. Binaries contain a mix of data and instructions. There's the data that the application uses, but there's also the instructions that our computer will run when it gets the application. So how do we tell them apart? How do we tell what's data and what's an instruction? We don't. Compilers take source code, they do something to it, and they give us a binary. And this binary has mixed in the data and instructions from the source code. But fortunately, there's a thing called a decompiler, which takes the binary, it does something to it, and then it gives us source code out. And so it is able to actually extract out the data and the instructions and give us back something that we can work with. So how do decompilers work? How are they able to decipher data and instructions all from a single binary? Well, decompilers, they output code in C, regardless of the original language. And the reason for this is that C is close to the machine code. It is very easy to translate back into something like C. Well, not very easy, but it is easier than translating into something like Python or JavaScript, where you're going to a much higher level language. And so why C? Well, it's just low level. It's close to the machine code. And it's important to note, though, this is not the application source code. The source code that our decompiler gives us is an approximation. We don't even know if the original code was written in C, but our decompiler will give us C. And there are issues with this. So compilation is a lossy process. We lose data by compiling our code. We lose variable names, and we also lose data types. And there are multiple ways to achieve the same result. So if something's an int or a long, it's still a number. We can still work with that. Do I use a for loop or a while loop? There are different ways to get the same result, and our decompiler has to try to guess which one would have been used. And there are compiler optimizations. It is very rare that the code that you've written will be the code that gets compiled. Compilers are really smart. They will see what you are doing, and they will decide, no, I know a better way to do this, and it will give you different code that doesn't even look like it. One of the things they'll do is they'll unroll a loop. If you have a loop that says run this 5 times, the compiler will look at that and say, no, there's a better way to do that. I will just have the same code 5 times in a row. That'll be faster. And the compiler will do that. And now the decompiler will have to guess, was this a loop or is the guy that programmed this just bad? So decompilers, they do their best and they are really good at what they do, but they need help. We need to sort of guide the decompiler by our best guess as to what something is, and we can sort of help the decompiler. So the decompiler gives us a guess of what it thinks it did, and then we can kind of refine that and then go back to the decompiler and have this sort of back and forth with it as we sort of refine what that source code could have looked like. And one of the ways we guide them is data types. We need to tell the decompiler, no, this doesn't look like what you've detected it as, and so we overwrite what it's done. And then there's also variable names. When you get code from a decompiler, it will have variable names like stack var4, which mean nothing. We need to have some name that we can actually use, and so we'll be renaming variables as we sort of figure out what they're doing. So we're going to be using ghidra. That's our main decompiler. Ghidra is an open source decompiler released by the NSA. I don't know if that makes it spyware or software by spies. I'm not sure where the distinction is. And it compares quite well against paid decompilers. So there's IDA Pro, which is a pretty pricey decompiler, and yet ghidra is able to compare quite well despite being free and open source. The basic workflow for using ghidra is that you create a project, you import a binary, You open the binary and just run whatever Ghidra's analysis is. Whatever Ghidra says it wants to do, just let it do that and then see what it comes back with. And then you just start reading the decompilation. You try to figure out what the code is. So you add variable names, and sometimes the variable name will just be maybe this. You don't know, you don't need to, but it sort of helps you refine what the code's doing. You provide data types, so sometimes it won't detect a string and it will instead think that that's just an integer, and so you'll correct that. And we also look up what we don't know. This is part of why we don't need to know C, is that we can just look up the pieces that we don't know, and that kind of fills in the missing knowledge. So what we'll do, the easiest way to actually learn what Ghidra is and how it works is to use it. So hopefully everyone has Ghidra set up and we'll be able to start decompiling an application together. So we are going to solve a basic XOR challenge. This is kind of the hello world of reverse engineering. And to do that, we are going to actually start the CTF, and we're going to solve one of the challenges in this CTF. So reverse engineering challenges often have a secret password or flag. So sometimes you enter the secret password and that will give you the flag. Other times the secret password is the flag. Our goal is to figure out what the flag is. So if it's solve the secret password and then you get the flag, or you just crack the flag, we're going to need to look at the application and figure out what it's doing. And the CTF should be available at this link. So I believe it's in the Discord, ctf.flinderscybersociety.org. And we should have a list of challenges that will need to be made visible in just a moment. All flags are in the format of CTF in capitals and then some curly brackets with something in the middle. When you go to submit the flag, submit everything. So start with CTF, go all the way to that closing curly bracket. Prizes will be awarded at the end of the night based on how many points everyone gets. And ask for help if you get stuck. Yes, there are prizes, but this is not super competitive. We're all here to learn. If there's something that's confusing or you don't know, just ask for help and we'll help. And one thing that I do want to say just now while we still have the slides up is there are a bunch of additional resources. If after tonight you want to pursue things further, I'd recommend the Ghidra book, which is a book all about reverse engineering, although it does focus on Ghidra. If you want to know about compiler optimizations, there's a great talk, What Has My Compiler Done For Me Lately?, which talks about all of the weird things compilers will do to actually speed up your code. And there's also crackmes.one, which is a collection of reverse engineering challenges. So with that out of the way, we can actually open up Ghidra and get started. But first, I will just need to reveal the challenges. Yep. Oh, of course. It shouldn't show anything too bad. Okay, cool. So what we can do, we will be downloading this basic XOR cipher. So if we open this, we should see a download for main, and that is just an executable for this. And at first, it should give you a window like this that looks absolutely hideous. I don't know who designed the UI, but it is a really useful tool despite how it looks. So do people have the challenge downloaded? Do you have Ghidra open? has not been analyzed. This data to tell us more information about it. And we just leave it as default. People far smarter than us have written these analyzers and have decided what should be run. We just leave it as default. We just click analyze. And now we have the main window of ghidra. And this is an absolute mess. There's a lot of information here, but we don't have to worry about most of this. The main windows that we'll be looking at are this symbol tree over on the left, the listing in the middle, and then this decompile window on the right. The rest of these windows you can just ignore. We won't need to touch them tonight. The first thing that we should do with a binary is we want to look what are the functions that are here. So if you've programmed in Java before, you'll know that you have your main method, and that's where your code starts. C is the same. There's a main method. That's where your code starts. That's the first thing we want to look for. So if you go into the symbol tree under functions, you will see a bunch of labeled functions. Some are just labeled fun something. The decompiler doesn't know the name for them. But here we see that there's a main. So we can just double click that. And that will now be opened in both our listing view, which shows the disassembly, and our decompile window, which shows the decompiled version. Now, we can just move our decompile window to be the main focus. And this is an absolute mess of just convoluted garbage that we're looking at. There's all of these variables that are declared, and none of them have any names. The decompiler doesn't know what they are. Then we come down a bit, and now these variables are all being set to something. This is random garbage. We're not supposed to understand what this means. We haven't begun solving this yet. When we're reverse engineering, think of it almost like a Sudoku puzzle. There are only a few numbers that are filled in to start with. The rest of it is just like this. It's random gobbledygook that we can't make anything of. But slowly, piece by piece, we're able to discover a bit more about how it works. And then from there, we sort of fill out our knowledge of what this application does. So as we look at this, the first thing that we see that's actual code that the application is doing is this. It is calling printf, and it's saying enter the flag. So presumably, this is just the prompt to the user. It's telling them enter the flag, and then it'll take in some input, do something to tell us if we're right or not. Now, the next line, things get a bit more interesting. We have PC var2 equals fgets, where we then have local 128, ox100, std in. But here, this is calling a function, so we can look up what this function actually is. So if you have a Linux system, you can just use the man pages from your terminal. Otherwise, you can just Google to look up the documentation of this. So to get the man pages, it's man, and this works just fine into Google. You can just type in the same string and it will work. So we want man, and we want section 3 of the manual. And then we want fgets. And I don't have the man pages. Of course I don't. I use Arch, as you can tell, which is why I don't have the man pages. It doesn't work very often, but it makes me feel better because I use Arch and you don't. But you use that? My man, my man. Do you use Vim as well? Nearly, nearly. Well, so long as you don't use Emacs, you'll be good. So now we have the man pages, and what these are is these are essentially a concise form of documentation for what every function does that we can use in C. If we have a look for fgets, it reads in at most 1 less than size characters from stream and stores them into the buffer pointed to by S. This is a pretty crude way of telling us what it does. Essentially, if we go up to here, where it gives us the definition, the signature of fgets, it takes in some character array, some buffer, some string that it will store the output in. It then takes in the number of characters that it should store, and then it takes a stream. So where is it actually reading this data from? If we have a look at this disassembly, so we're reading from standard in. So standard out is where text gets printed to when we display it in the terminal. Standard in is where text gets read from. We are then reading OX100. Now, just to make that easier to see, I will right-click on this, and then this gives me all of the conversions that I can use, and I'm going to pick decimal. And we are using fgets to read 256 characters from standard in, and we're storing that in local 128. What could local 128 be? What is this variable? Yep. Yeah, exactly. So this is like the input. This is the user input, right? So what we can do, right-click this, rename variable, and I'm just going to type in user input. And just like that, we can see that's changed in a few other spots in the code. So we're starting to get some. This is only our first variable name. This isn't quite enough to figure out what this application is doing. But there's something else we can learn about the user input as well here. So if I'm storing 256 characters into the user input, well, then I can figure out how long user input is. User input is, well, probably 256 characters long. So to add this information, right-click on the user input again. This time we'll retype variable. And at the moment, it's an undefined A. Ghidra couldn't infer the data type because that's lost when it's compiled. Data types aren't real. But by looking at this code, we're able to figure out what the data type would have been. It would have been HR 256. So a string, essentially, that stores 256 characters. Press OK. And now our decompilation has changed quite a bit. I'm now staring at a bunch of user input something equals 0. What this is doing is this sets the value of that character to 0, to a null byte. In C, a null byte is the end of a string. So we have some amount of characters. When we reach a byte that is just 0, that means stop. That's the end of the string. And now our decompilation almost makes a bit more sense. This is still really weird. Why is it just, there's no shorter way to set all members of a string to 0? But now we have this. This sort of makes a bit more sense. So we print out, enter the flag, and then we store whatever the user types in into a value called user input. There's still this PC var2 that we're not quite sure what is. If we look back at the man pages, we'll see that fgets returns S on success and null on error. So fgets will either return us some data or null, which is just 0, if it fails. And if we have a look at this function, we can then see that this value is then compared with 0. If it is 0, there was an error. It says there was an error reading the user input, and it does something. But we don't really care what it does. It couldn't read the user input. That's fine. We want to see what happens when it can read the user input. What's the flag? So we can just rename this variable as well. So we'll rename variable, and this will be fgets result. Does everything sort of make sense so far? Okay. Fantastic, Sid. Thank you. I like the enthusiasm. Now, let's look at the next bit that we see here. So this is svar3 equals stir cspn user input and then \r \n. \r \n, those are new line characters. So on Linux, it's just a \n. On Windows, there's a \r and then the \n. But this is some new line, and it's going into stir cspn. I don't know what this function does. How can I know what this function does? I don't know C. I don't know what this function does. Man pages, yes. Of course, it's the Arch Linux user who knows how to read the manual. So we just man, and it's section 3 again. and it's stir c span. And you can just type this into Google. A lot of websites just host demand pages online. And what we look at, so there are two definitions. The first one is for stir span, which takes in a character pointer, a string s, and then has an accept string. The one we're looking at though, stir c span, takes in a string and it then has a reject. So let's read what the function actually does. So the stir c span function calculates the length of the initial segment of s, which consists entirely of bytes not in reject. This is a really fancy way to say it just tells us where the reject happens. So if I say, hey, reject a new line, it will tell me where that new line is so that I know I can avoid it. And it returns the number of bytes in the initial segment, so before that reject pattern. So this value is the position that there's a new line. So this would then become, and there I just pressed L to rename the variable. You don't have to right click, you can just press L. And then this is position of new line. And then we see on the next line, we say user input at position of new line equals \0. So that's that null byte again. We're just saying the string ends here. Wherever that new line was, okay, that's the end of the string. Don't worry about the rest of it. Does this still sort of make sense? It's about to change. So now we have this big block of code. So we set local 14c to 0. We then have while true, the position of new line equals strlen of user input. So maybe this isn't the position of the new line. What this is a compiler optimization. Compilers are smart and they realize, hang on, you've stopped using that variable from before. I'm just going to use it for something else now. And the compiler will just repurpose variables because it knows what it's doing, you'd hope. And it'll just make those assumptions for us. The decompiler can't make those assumptions. It has to try to guess what different variables were. Then we have this if position of new line -1 is less than or equal to long local 14c break, and then user input at some position is XORed with itself and some value. What we can do is we can just sort of take this slowly, and we don't know what this is doing as a whole, but we can sort of poke and prod at individual pieces of it. So here, this position of new line, this isn't actually the position of new line. Here, it's the length of the string, and so I will just say position of new line and string length. When we're decompiling, it's actually really good to have long descriptive variable names because all of this is random garbage. This is gobbledygook. It means nothing. So we want to try to increase the ratio of human readable stuff to gobbledygook. And so having really long descriptive names where we know exactly what something's doing is one way that we can do that. Now, as we look in this loop, there's then this if, which if this condition, it will then break. Then there's user input at that local 14 equals user input at local 14 XORed with OXB6. So there's some kind of XOR cipher here. And then local 14C equals local 14C plus 1. Now, this bit of code smells really bad. There's something weird about it. Why is there a while loop that has some variable set to 0 at the beginning, then in the loop, you check that variable with another variable to see if you should stop, and then you add one to the variable. This doesn't seem like a while loop. What type of loop would this have been? For loop. So if this was a for loop, then this local 14, this would have probably been called just I in the original code. But to give it a slightly more descriptive name, we'll just call this iterator for XOR, because this is based on where we're actually, this goes through the string as we XOR whatever the user entered with OXB6. So we're doing something to the data with our XOR. And that means that this if what this is this is probably just the range check in a for loop. What this would have originally looked like is, in I equals 0, I less than string length, and then I++, but because it's been compiled and then decompiled, we've lost information about this code. And so now this is the decompiler's best guess about what it would have been originally. Then the next part of the code, position of new line and string length is set to the string length again. And then if the position of new line and string length equals hex 15, I'm just going to change that into decimal so that it's a bit easier to see. So if the end of our string, if the string that we've entered is 21 characters long, then we do stir incomp local 148 with user input, and then hex 15 again. Let's just change that to decimal again. So I don't know what stir incomp does, so we just go to the man pages. We don't need to know what this does because we can just check the man pages and see. So we just man, section 3, string compare. This takes 2 values in and then a size, so it knows how big they are, because remember, C is not a memory safe language. We can go past the end of these. We need to know how long they are. And what it returns, 0 if S1 and S2 are equal, a negative value if S1 is less than S2, and a positive value if S1 is greater than S2. So it's kind of backwards. 0 means the two of them are equal. So let's see here. Here we stored that in some comparison result. And then we check if the comparison result is 0. So if they're equal, we go to this label. Yep, and we say correct. So here, what are we actually comparing to? So we have some other input part. We take in some input. We XOR it with something. So we've got our input. We've done something to it. We've now compared it with something else. What are we probably comparing the input with? We ask the user at the beginning to enter the flag. Yep. Yeah, so we'll be comparing this against the flag. So what we can do, this local variable down here, we can just press L to rename it, and this is the flag. There's something else we can figure out about the flag as well, though, here. We are doing a stir in compare. So string compare of a certain number of characters. We're comparing 21 characters of the flag and the user input. What can we tell about the flag from that? Yeah, it's presumably 21 characters. So what we can do, we can go up to the top here. And here, flag is just set as like some garbage. If we right click it, this is still garbage. There's no way to represent this because ghidra got the type wrong. It doesn't know what this data is. Based on our assumption about what this flag is, what data type would this be? So it's 21 of something, 21 chars. This is another string we're comparing with. So we'll retype variable. We will call this a char 21. And now here we're seeing that there are some weird minuses in here. We wouldn't expect to see minuses in letters. And the reason for this is because characters can be signed or unsigned. This is ciphered data, so this isn't being stored, right? This is actually a unsigned char. So we just right click on flag again, retype variable, and we just make this an unsigned char 21. And now everything makes a bit more sense. We have all of these values. And at this point, we kind of have the flag, right? We know this is the flag variable. It stores these values. But if we try to actually right-click these values, none of them are characters. And that's because this is the encrypted flag. We have to decrypt this flag in order to be able to actually read it and see the output that we could submit. There are a few ways to decrypt this flag. The easiest way is usually to just write a bit of code that will decipher it for you. You could use an Excel spreadsheet if you feel so inclined. But what we can do, we can just copy all of these parts that set the flag to 0. It's kind of an ugly way to do it, but it works quite well. We just take all of these, we copy them, and then we can go into our code editor. If you want, that's VS Code, or if you're a nerd, Vim. And what we'll want is, I'll just use Python for this. My man, that's my man. You're like the one other guy that's actually heard of this editor. Everyone else is like, oh, is that NeoVim? And I'm like, no, it is not. It is completely different. But I'll use Helix. I hope you are too. And we just need a simple Python script that we can use to decipher this data. So like this, we can then paste our data in. And as it is currently, this is just setting the different positions of an array. There are a few ways that we can clean this up. You could quite happily just by hand go through and just delete everything before each byte. You could use multi-cursor if you want to be a bit fancier to sort of select everything that you need. You can just drag the mouse. VS Code has a bunch of multi-cursor, but it doesn't matter how you do it. What we're after is that we can just sort of clean up all of this so that we just have a list of values. And what I'm after doing is I just want a list. So in Python, we just have all of our values between square brackets. Then I'll just call this flag equals this list. And this is all of those bytes. When you're sort of reverse engineering a challenge, especially in a CTF, you will have some absolutely hideous code where you've just like ripped the flag out of the binary, chuck it in Python, or sometimes you'll even use C because it's a bit easier with the bitwise operations. And you will just start clobbering stuff together to get something that works and can actually decipher the flag. Then what we can do, we need to decipher this data. So I'll just use a list comprehension because they're short. We'll say flag equals, and then I'll just say byte. And here we actually need to decrypt the data. So whatever our executable was doing to this data, we need to do the same thing so that we can actually get it as the flag. So here, what it's doing, it is XORing the user input with OXB6. So XOR is a reversible operation. So we can just XOR this with B6, and then we should get the input data. So byte XOR OB6 for byte in flag. And then we can just print out the flag. In theory, we have all of the bytes that make up the flag. We are now doing the same thing that the code did to them. So we're XORing them with OXB6. When we print this out, we should, in theory, get the actual flag output from here. When we run this, we get a bunch of numbers. And that's probably not what the flag is, right? The flag's meant to start with C, T, F, and then something. And that's because we're just looking at these as numbers. We want to look at them as characters. We want to interpret this data differently. So here, where we do this by XOR 6, we can just change this to CHR. In C, HR is 4 letters. Char, there's an A in it. In Python, they just got rid of it. So we'll do char. This byte XORed with OXB6. And this is telling us, look at the data as if it's a character. And so now, when we run this, what we should see, is we should see the output. And this is still a bit ugly because Python's just printing the array. If we want to clean it up, we are seeing the output correctly, I believe, or slightly less of it. I copied it across wrong. what we can do, we can fix this flag, and what we'll do, just do 2 opening ticks, so we create a string, dot join the flag. And this is just a Python way to say, take an empty string and just merge all of these characters to it into just being one whole string. If you copied the data properly, unlike me, what you should have is a complete flag. You should see the flag all the way to the closing curly bracket. I copied the data wrong. I was impatient. I didn't copy everything. And so I'm missing the rest of my flag. So you can see the start of the last word. If you do see the flag, go to the CTFD and you could submit that flag to get points. Otherwise, you can bear with me as I try to copy the data properly this time. Do you see the data decompiled like this? Because I just realized I made a mistake when reverse engineering this. I got ahead of myself. This data, we didn't actually reverse properly. We see that all of this looks right. So this, flag 0 to flag 15, this looks fine, but there's still this garbage down at the end here. And the reason for this is that we actually set the data type wrong. How? The flag was 21 characters, right? In our mem compare, we are comparing 21 characters of the flag. But in C, strings end with a null byte. There is a secret character on the end of our string that is just 0, it's just null, but we still need that to tell our decompiler. So let's change the type of flag. So we want to retype variable, and instead of a uchar21, we need to account for that null byte at the end. So let's make this a uchar22, and now we can see that the rest of our flag, that garbage has gone away, and we now have extra values in the flag. And so now if we copy these across and cut them up the same way, there are prettier ways to cut it up, but if it's stupid and it works, it ain't stupid. Just paste these in again. And in Python, we don't actually need to worry about a null byte. I'll keep it in there just because that's how the flag had it originally, but we don't need this. Python knows how long strings are, so keeping that null terminator around isn't actually needed. So now that we've copied in all of the flag, and this is the same code that we've had before, we just need to make sure that we have all of the flag if we want to see all of the output. Now, when we run this, what we should see is the flag. And we don't have it. Because when we copied the null byte, just to show, this is why we don't really want null bytes in Python, is because this is stored as a string. Python doesn't want that. Python just wants the bytes of the string, so we can just delete the null byte. Save it. And now when we run it, 3rd time's the charm, we should see our complete flag. And so now if you go to CTFD on the website, you can then submit this flag for the basic source cipher, win your points, and then we have other challenges as well. Has that worked for anyone? Did anyone get stuck with that? Does that make sense? No one's saying it didn't make sense, so I'm just going to pretend that means everyone understood that perfectly. Now, we do have pizza. The CTF is open, so feel free to start working through other challenges. Over the course of the night, I'll go through a few other solutions with you. Start solving challenges, have pizza, and if there's anything that you get stuck with, just ask for help, and we're happy to help out on solve challenges. Yes? Yep.
Easy. Come down every month. You want it. No plates, we've got tissues.
Flinders content.
I think that's the one. So, do you have a sort of connection? I don't know if that's it. My job. So I mean, yeah. Pretty fun. Yeah, pretty fun. It's like breakfast now. The exact same thing as even I did at night. I was like, oh, yeah, I think I'm a little stuff. It was like 40 plays machine, like bleep it out, and then 2 hours fine, like the tiny little place. She's not wasn't in there. It didn't realize this was going out, and that's wondering if files. One of the folders is one file, and then one file is one section, but as multiple files, multiple things. Someone actually go to the bus. No, so that's not that. Oh, yeah,
So we're talking about true
yeah, you're supposed to find the admin column. It's supposed to work. No, it didn't and also, like, that's also like that's how they did it.
Holy Barb's talking to so I can, yeah, what was nice.
It was like 10% of your
The mix of my team I saw thing is the perfect mix of run and mouse high. That's two polar opposites. It's horribly inefficient. Yeah. You do need to see how it's going. Well, you can't take it out of that. It's just massive. And it runs screens on it. Oh, that's yeah. Strings won't actually show you. I think it's 8 words in the challenges for them, but kind of create or something.
What's a wide character?
How can you have to 6 weeks?
Yeah. I was finding the one with from the router to a PC. I was trying everything. And I was like, and I'm like, and I do my switch setup like once. I mean, there should be more practice. But making that like push me forward and not because I just didn't know how to do the closing stuff. Yeah. Just got the right stuff. Everything like that.
Yeah, people call me character.
I got yeah, I don't know. I feel like I wasted so much time on this call and then so far. But I was like, yeah, it didn't feel like it was a test.
So they you take
a lot of stuff.
So do you have to type the password in by hand?
I think I'm not messing it. That I can mess it, you can
Awesome, that's
the room. Yeah. I don't know.
yeah.
Just discouraging.
I use Task purely because it works without internet.
I understand some of the theory stuff, but it just feels so loaded at the end of the day. I don't know theory tests. Because so it covers such a yeah. It goes really
Some people Bitcoin miners in the market, so I assume that's also on something. Hopefully someone else in that it turns out the lockers that have alphas raise money Bitcoin. That's what I said. So if you mine in there, plug in also raises.
IPv6, like stuff, and I was one of the students that kept on like nailing it. So I mean, like IPv6 subnetting, IPv6. Yeah. So I wanted to tell you about like. I think I understood like the whole layer model like really. I got that really down. And I could understand all the components and everything. Yet there was no questions like about what does this I guess do as an every checker? So I thought it would be like, oh, that's the model. Yeah. Down that. Whatever else. I have no idea what it was. Yeah, it's like local connection, like it's constantly, I'm pretty sure. So I looked it up, like, oh yeah, it became constantly like a few years ago. Sorry. Yes, yeah. Honestly, the start of this year was like so like I think like if I was this kind of thing, I would have actually done it this year. I'm not against so much stuff. So one stuff that I do on my team, the other three excellent stuff like one I got obviously like trying to go to like what am I doing is related to what I'd like to do, and then I'm like, okay, we've got data engineering labs, like sorting data sets, that's all graphs. Like it was very like for the third year subject. Yeah. Yeah. I didn't put much subject. I don't remember. I don't think I learned much. Okay, you've got to be a positive, right? Yeah, okay.
Yeah.
What do you want to do? Yeah. So I went to the bomb place.
And then you go into one year and yeah. And like you color the things and you pull it out and you don't pick it again. I think so. I mean, I'm sure on the weekend, I think for the most part, like I'm not much exams yet. I'm just gonna like I know the general question is not like a specific thing, like I'll have it. Yeah. But no, after the practice exams, I'm pretty I mean, like all the materials you need to do well, so if you don't do well, you kind of only have yourself to blame. So I've done really well. Out of curiosity, what type of test is I'm gonna see it. I don't know. I'm gonna check my schedule again. See if I can go out. Robotics. Is it the robotics one? Like next semester. We'll see. And I just remember that like it's doing processes, but like it's actually like classes. It's like well, you have your required 18 or IT Like you need to just take your video, just 10 different variations of every single idea. But there's like 84 laws. It's just like each different, what are each different laws? It's just like one tiny plastic. Sorry, I'm so sorry. They're all retired as yeah, it's not all of the good skills. Yes, you probably know more than that. We don't have one on my head. I'm also on this plan where they're just staring at camera. Like, while I'm just hanging out and just pop it or something. Yeah, maybe. So that's why you're just in case you're zero. The exact same thing. It's very mature. It looks like a cheap program. Yeah, because it doesn't actually build the code. You know, again, you put the thing out. What you do is when you rename colleagues, you try to like read it and rename their names and rename and read it. Oh, right. Okay, so like, I'm sorry, I think that's it. Yeah, you can rename it. What I guess is so you go to you basically just try to figure out like what at the end of the so that it's changes yeah, basically this is like the variable that then showcases. So what if you look up F is a predetermined function. If you look that up, it reads and stores like variables. Like so it reads a variable and stores it for something. So either does that read it reads and stores. So then you can look at the answer to that the whole code and you can see where it's getting its read and store. Yes.
Oh, yeah.
How we going? You feel like you're better with life. If you're amazing.
Just like how this is. No, it's also Oh my God.
Getting your head around it. That's totally cool.
That's cool.
Just to prove it. Yeah, I'm like doing the alien she's actually quite CTF are pretty difficult. I'm working my way through the and then it says to me to ghidra. I tried on the VS Code and sometimes you do ghidra. Oh, okay. Yeah, but long cables it's all the source code. You can actually download both files. Yeah, I mean, it's used.
Oh, yeah, I'll see if I can get to... Oh, this is my laptop, so I'll stream separately to you. You don't have my laptop. So I'll stream separately to it. Oh. Oh, all good, Emmanuel. To check my screen up. Thank you. Cheers. Oh. Sorry. Yeah, I'm not sharing my screen. Cool. Cool. Should be there now. Cool. All good to take the pizza banner off as well. Yeah, all good to take the pizza banner off. The pizza banner. Cool. Cool, thanks. All right, cool. Hi, everyone. Who's feeling a bit lost, potentially? I'm going to go through a really easy challenge, and it's all in Python, and we don't even need ghidra. And it's really simple because I wrote it, and I don't know how to use ghidra. So we're going to go through that. So the challenge that we will be doing, and you can follow along with, is called Long Cat is Long. So if you want to follow along, feel free to grab it. So I'm just going to download both files, save them in my Longcat folder, and we'll get started. So I'll be using VS Code for this one. Feel free to use whatever you'd like. And we appear to have two files here. So we've got a Longcat, and it looks like a big Python file. So have a go at that. And then the other file here is a picture of Longcat. So we'll start working through that as well. So the first thing that I like to do is when I get some code that I'm reverse engineering is actually run it. Let's see if it runs, let's see what it does. So we can do Python Longcat is long, And we can see here it wants a pin. So, you know, all right. I don't know what's happening, but let's see how it works. Incorrect password. Ooh. So we've got something here, and I'm guessing I'm going to need to enter the correct pin, but I don't have the correct pin. But what I do have is all the source code. So if you kind of think about it, somewhere in the code, the pin is here, right? The pin's somewhere here, like it's checking something. So maybe we can find out the pin, or maybe we can just kind of get straight to the flag. That's better. Cool. So as we can see here, nothing's named very well, is it? So we've got a bunch of meows. There's a mew here. There's a bunch of arrays. We're reading in a file here. You can tell that, but it's called meow. So maybe let's just start working through it, and we'll see how we go. So one of the things, I'm probably going to go through quite the slow way, I guess, and we'll kind of understand what's happening. So one of the first things we can do is we can kind of spot parts of the code that we know what it's doing. So as I identified before, what do we think this function's doing right at the top here? Does anyone have any ideas? Might be pretty simple. Opening the image, yes, cool. So one of the things we can do is we could you know, not rename anything, and we could, you know, go through. But VS Code actually allows us to like rename a function really quickly. And we can call this, you know, now we know, oh, is Copilot going to solve everything for us? No. I'm gonna name this one read in image. And now we can see that, you know, where else is the image read in? Oh, it's read in right at the bottom. And then we can kind of keep following it around. So, okay, well, if meow equals read in image, what do we think meow stores? Probably the data from the image, right? So, you know, let's slowly go through and rename this one as well, right? So, okay, what's this one going to be? Image data. Okay, where's image data referenced? Oh, all the way up here, cool. All right, now things get a bit more interesting because, okay, what happens here? It's not completely obvious. Maybe it is. So this function here, does anyone have a go? What do we think this function here does? Let's break it down a bit more. What do we think this does on line 20? Get it. What is image data? What type is it? Or what do we know when we see square brackets in a programming language? Array. Who said array? Yes. Fantastic. So it's an array. So we can probably assume that meow, I'm going to keep saying meow. It's going to be for all of these. This meow here probably takes in a number and it returns the thing that is at that point in the array, right? So maybe let's name this one look up in a, you know, what should we call it? Cats. Maybe. Look up data from image. Cool. So, you know, reverse engineering, you know, we can start going through code and we can start pairing what we think we know with what it does. And we can start naming things properly. And we can do this with the whole file, right? But we can do some other things as well. We can edit the code so we can actually see what runs. You know, you could do this in the debugger as well, but I don't think I've got that set up. But what we could do is we could do print test1. You know, when does this function get called? Okay, let's run it. Does test1 pop up anywhere? Oh, so it looks like maybe when I get an incorrect password, test1 is set. So I think that is incorrect password. Okay, so incorrect password. Okay, incorrect password. All right, maybe we've hit something here. And okay, well, if else is incorrect password, maybe this is what happens when there is a correct password. So let's take a look at this. And maybe we could assume this function here is check pin. Maybe that makes sense. Cool. So we've got a comparison here. So we're checking if two things are equal. So if you kind of think about it, we're checking where the pin is equal somewhere. So maybe this could be it. So what if we print out, you know what? I want to print this. What is this? What did that print? One. That's interesting. What is that? So what is our other one? Oh, is that the pin? I don't think this challenge should have been this easy. If that's our pin, that would be nice. Oh, cool. Whoops. Cool. So see how we could kind of go through the code, we could have a look what's going on, we can modify it, we can print out values at certain points. Obviously, if you have a debugger and know how to use a debugger, that would probably be quite easy. We'd see a pin, you'd be able to grab that, but looks like I just grabbed that. So yeah, whoops. Probably shouldn't have been that easy, but there's the answer for Longcat, if anyone's looking at solving that.
All right, so what I'm going to do, I'm going to go through another one of the decompilation challenges. If you're working on something and you just want to finish working on that, feel free. Otherwise, I'll go through one of the challenges and we can see what it looks like. So what I'll pick, I'll go with slide to the right. The points for each challenge loosely set the difficulty of it. So Wawa and stagnant study are two of the harder ones. Slide to the right is pretty simple though. So we'll download this. Yep. Oh, yes, of course. That's what people get for getting it online instead of coming in person. So what we'll do, I'll close out of the XOR challenge and we will import the new one. When we open it, just use the default analyzers. The only thing that you might do when you open ghidra, the only way that you might change these analyzers is to select all of them and just run everything, even the experimental ones. Usually you never want to disable an analyzer because all of them are really useful. So we look at our functions, we're looking for main. We don't actually see a main function listed here. We see a bunch of fun with something, but our computer always needs to know how to start this application. And that's usually with an entry point. So here we see entry. We can look in that. And that's calling a function that is libc start main. Well, probably this is going to start the main method that we have. And it takes one function in. So if we open this, we can sort of assume that this is the main method, but let's have a look here. So it's doing stuff. This looks kind of similar to the XOR challenge with all of its initial setup. And then here we see that it's asking enter the flag and error reading user input. This is probably the main. This is going to take the user input and do something with it. So here we see fgets again. It's very common to see these functions show up all the time in C because these are just the default functions that you're given. You don't have to rewrite this yourself. You just use this library function. So I know that fgets from standard in, that's going to be reading user input. So I'll change this hexadecimal to decimal. And so then I know that this is going to be the user input. And I also know the type of this. We're reading a string. This is going to be a character array. We're reading 256 characters. So this is probably a 256 character array. And so we can retype this as well. And our assembly, or our disassembly rather, has just gotten a lot messier, but that's okay. This is just initializing all of this data to 0 like the XOR challenge. Again, it checks if there was an error reading the user input, and we can just kind of skip past this. And again, it cuts off, it uses stir cspend, it cuts off the end of the string, it cuts off the new line. And this is, again, something very common in C programs. When they take input, they want to get rid of that new line at the end. Whether that's Windows or Linux, that'll be different. That's why it's \r\n. So then this is going to be the position of the new line. We set that to a null byte, which is very common to see. As you're cutting up strings, you just insert null bytes just to sort of terminate a string. And here we're seeing the same sort of pattern. We see this local 14 equals 0, a while true with string length again in it, some weird comparison. We do something with our string, and then we set local 14 equals local 14 plus 1. This is how for loops will often get decompiled. You can almost always assume that this is a for loop that's just been decompiled badly. So local 14 is going to be iterator. And here we're doing something to this string. Here we are seeing user input at iterator times 2. how are we multiplying a character by 2? This doesn't make sense, right? I can't have like A times 2. That's not how characters work. What this is doing, this is working on the bits of the number. So a character is just a number that's been interpreted in C by ASCII. And so this is multiplying that interpretation by 2. So our user input, each byte in that is doubled. And I will make a comment of this because that's kind of weird behavior. I'm not always going to infer that. So I'll just click on iterated stop at the very top, and I will go down to comments and set pre-comment. And I'll just write multiply user input by 2. And then what we're doing, we get the length of it again. We check if the new line is at 28. So we check the length. This is 28. This is probably also going to mean that the flag's 28 because we then do a mem compare again with 28. Okay, so we can kind of infer that this local 148, this is the flag. It's a character that's 28 long. So I will call this flag. I will retype it to be HR28. And let's have a look at this. So here we're seeing minuses, we're seeing weird things. What that means is that flag is actually going to be an unsigned char. So we'll just right click on this, retype, and this will now be a uchar. And now we see only whole numbers, and we see some of these are interpreted as letters, and some of these are just bytes. Our characters are multiplied by 2. So what we can probably do, we take the flag, we divide it by 2, and then that gives us the input that we would enter. Now, just because it's a bit interesting, why is this multiplied by 2? Does anyone have any guesses at why this is a multiply by 2? This is a decompilation error. The decompiler could not figure out what this is doing because of compiler optimizations. If I have a binary number, every bit in that number doubles as it goes along. So if I bit shift that number one place along, it doubles. Because what was in the ones place is now in the twos place. What was in the twos place is in the fours place. So a bit shift and doubling or halving the number is the same. What this could have been is this could have been a bit shift that the decompiler saw as a multiply because the compiler will swap the two. It's faster to bit shift than multiply, and so compilers will replace that. So this is a decompiler artifact from bit shifting. So what we can do, we can take this flag, and now we need to bit shift it. We could do this in Python again. We could do this in C. We can copy this, and then I'll see how I go doing it in C. So let's do main.c. It doesn't matter what language you're using, so long as you're using a language that you can work quickly in and you know, that's fine. You can do this in an Excel spreadsheet. You could do this by hand. I wouldn't recommend doing it by hand. So we need a char flag that is 28. We then set all of the different parts of that, and let's just and because C is a questionable language, I need to actually add a null byte at the end here so it knows where the string stops. So this will actually be a char 29, I believe. And then I'll set flag at 28 to 0. And that is not it, because we haven't done anything to this flag. We've got the flag, we've got it, but now we need to undo that. The code multiplied, so we need to divide. And so what we can do is for 0 is less than 28. We're just iterating through all of the characters. We need to undo what that binary had done. So we'll say flag at I, it was flag at I, divided by 2. The code multiplied our input by 2. So presumably we divide the flag by 2, and we should get the same result. If we compile it, we run it, and we are still not getting the flag. What have I done wrong here? What I want to do is, let's do a bit shift by 1. So when the code is doing that multiply instead of that divide, that's just a bit shift. So it's just confusing bit shift and multiply. So let's see if this is it. Otherwise, I'll need to think about my code, which I don't want to do. No, that's a shame. Where are we going on? So we have our flag. We know what our flag is. We know what's happening to the flag. It's presumably, because if we look in our disassembly, our flag is compared with the user input. The user input is doubled. That's then compared with our flag. So if the flag divided by 2 equals our user input, then that's probably the right flag. So let's see. Looks like we copied the flag across properly. I'm a bit confused by why this isn't working. In theory, it should. What I'll do, I'll try doing this in Python, and we'll see if we have better luck in Python. Maybe not. Here, where there are characters in this array, what I can do is I can write odd, and that tells us what this character is as a number. So instead of actually needing to go back into ghidra and manually convert these, I'll just write odd. And in Python, you might be a bit confused why I'm leaving the semicolons. Semicolons are fine in Python, and they actually do still mark the end of a line, but they're completely optional. If you just go down to the next line, then it will be assumed that that's the start of a new statement. Let's see, and if we print, what I want to do is I just want to check the bytes that we have here. And often when you're reverse engineering, you'll see something and you'll think you've sort of got it, you know what it is, and it's just this last step of just reversing it and re-implementing the logic can really slow you down. So this, helps if I write the Python code to actually run. So now we have a bunch of characters. This is looking a bit better. And so let's, I'll just do a list comprehension again. So now we're getting those characters shifted. So this should be the flag, but we haven't given it the correct data type. We're seeing this as integers. We want this as characters. So let's change this again to char. So we'll convert these. We know they're characters. The computer doesn't though, because the data types don't actually affect the data. And so now if we run this, now we see the flag. And to just make this neater, what we can do is we can just do 2 ticks dot join the flag. And now when we run this, this will take the string, merge all of the characters together, and we get the other flag. So this is a bit interesting though, because we see a decompilation artifact in our code. These are called decompilation artifacts because they're artifacts from decompiling. This wasn't in the compiled binary. The decompiler got it wrong, and it sees this as a multiply. But when we solved this, we just used a bit shift. A bit shift is the correct operation to use here. And because ASCII is a 7-bit encoding scheme, you can just kind of shift it over to the other unused bit in your byte. Did that one make sense? Yeah, okay, good. I got a thumbs up. That's good. Perfect. Sure. I haven't done any sort of classes in my sister. That's mostly where it's programming in front of people in real time. Oh, I have to get it. Yeah, that was. Yeah, plus it was end of that stuff. No, yeah, it depends. I'm the only dedicated cybersecurity guy, so I do training from policy to compliance, setting up automatic upgrades,
Yeah.
I'm accountable for it, so yeah.
I still have that now, like that. Against like how like America and like they're rushing out. It's like, hey, look at this. Yeah, they do a bunch of things. That's a bunch of like. I can, you know, I can get updates from email account, you know, message the spring and just saying, yes, financial report, Well, we and even if yeah, I mean, I have to say my main setups. It's just really it just forgets. Forget things out, you know, in the French translation of Harry Potter, they say they fix it. It's the same. Forget. Yeah. I know everything about that. Who founded it? Tonsley. It was created in a lot of different countries. There was some of them like renowned for like native countries.
Yeah. Yeah, they're one of the.
I was gonna say, just like this get up and dumping some concrete village. This is sweet. It's like a real side of that happens when it's like the American world.
still a couple of us, and
Have like a play into making sure it's originally they used to make only like sort of round.
yeah, no, I'm like, yeah, two of these actually.
And it's sort of just basically I think it was like
Well, yeah, I can everyone. The Bible has a, like, yeah, between that and store.
yeah.
Yeah, the trifecta is security. Once it is store, it's the, that, what's your name? Yeah. I think Ashley's plus factor.
Cool. We might finish up in 5 minutes, so get your flags in, team. Woo.
Actually, right now,
Sure, thank you. Cool. Submissions are frozen. Whoa. Cool. Lance, do you want to do prizes or am I doing it or up to you? I can? All right, cool. Alrighty. So, firstly, we want to thank everyone for coming. I think we are going to do a random wheel as well if you are here and you didn't do too well. If you submitted at least one question and got some points and you're on the leaderboard. Does this look right? Is everyone on here that submitted points? Cool, awesome. We'll also do a random wheel as well. But do we want to go through the prizes again? Do we want to? Cool. All right. So we have a prize here. This might be first prize. We have a nice GitHub statue right here. It's boxed like an Apple product. If we like those, it's very cool. And then we also have three separate vouchers, 1 month each, of Try Hack Me credits to get rid of as well. So that'll be for online people as well. So I'll refresh the leaderboard, make sure we're up to date. But yep, cool, easy. I'd like to invite the first place Person in first place, you in first place? Is that you? Fantastic, come down to the stage. Thank you. Can we get a photo of you being presented the award? Fantastic, Emmanuel, cool, thank you very much. Oh, you do want this one, right? Correct? Oh, fantastic, all good. Cool, congrats, good job. Cool, so now we have the months of TryHackMe. Does anyone not know what TryHackMe is? It's okay if you're not sure. Cool. It's a really good learning tool online, and it will give away a few months to 3 people. So go ahead and get rid of that. Fantastic. So I will now spin the wheel. YF Wong, fantastic. Congrats, cool. I don't have anything to present you here, but I'll take a note of this one, and I'll send an email to you with the voucher. Fantastic, easy. So, fantastic. 2 more. Boop. Riri123, hey! Congrats. And last one. Travis. Cool. Congrats, you 3. And yeah, thank you all for coming. Thank you very much to Lance for this amazing workshop in CTF. He made all the challenges. I'll go ahead and unpause the CTF if it's something you want to have a look at over the weekend, maybe into next week as well. We'll keep all the challenges up, and I'm sure we'll have some kind of write-up, maybe submitted, available online, potentially, cool, or at least all the answers, and maybe you can work backwards. But yeah, thank you all for coming. Hope you enjoyed the pizza, and have a good night. Thank you.